So our speaker today is Stefano Conversi. Stefano is a PhD from the Environmental Infrastructure Program, and he's from the 37th cycle, if I'm not wrong. He's working in the GeoLab group under the supervision of Professor Carion, and his research tackles the analysis of environmental data obtained from remote sensing techniques. So with this, I just leave the floor to Stefano.
Thank you. Thank you, Chiara, for the introduction. Good afternoon, everyone. Today I will talk about the integration of optical and remote and radar imagery to enhance river drought monitoring. And first of all, I want to state a little bit the framework of my PhD. I'm here between a partnership between Regione Lombardia and Polytechnic di Milano. Specifically, I'm assigned in the side of Regione Lombardia to the unit that is in charge of managing and monitoring biodiversity policies. While here, I'm part of the GeoLab, so I'm part of this laboratory for geomatics and Earth observation that is working both with software GIS, so we know that is the acronym for Geographical Information System, and with remote sensing data. Specifically, I'm working within the context of regional strategy for sustainable development. So specifically tackling the 15 SDG, that is the life on land. And the idea in this project actually is to use all the expertise that we can find here from Politecnico and also from Regione in order to produce something practical that can be used by Regione Lombardia. And here you wrote what is for now the draft of the title of my thesis, that is the application of remote sensing techniques to support biodiversity risk management and policy drafting in the Lombardy region. Specifically, I'm involved in two projects. The first one that is related to the identification and delineation of invasive vegetation in Lombardy lakes, and the other one that is the one that I will present to you today, that is related to the drought monitoring and specifically to river drought monitoring in the case study of Po. All of this is meant to be done through remote sensing instruments, and we will see which instruments we will consider. So, first of all, a brief overview of what we will see today. So, we will have an introduction on the drought event of 2022. We will see something for remote sensing for river monitoring, so how it is applied until now, and the new methodology that we are proposing for sensor fusion. We will go through the Po River study case, and then we will see obviously some kind of results of our water detection processing, and then we will also address some kind of future evolution towards the process automation, and then we will discuss a little bit about the conclusions. So, first of all, we know that Italy and Europe, more in general, suffered a big period of drought in 2022. Specifically, we can find actually these evidences both for Europe and Southern Europe in particular, and also in northern Italy. And what we can see is specifically that we have lots of different factors that concurred actually to the origination of this kind, or to the origin of this kind of event. First of all, poor snow accumulation during winter season, adding that led actually to a decrease of water supply from snow melting, and then also a consistent lack of rainfall during summer that obviously resulted in this exceptional drought event. We have lots of indicators also in the Italian territory that are stating obviously the critical situation in which we were. So we can recognize that Piedmont and Lombardia region mainly were actually affected by the phenomenon, and that more or less, we can say actually the biggest part of the Po River catchment were actually interested by this kind of phenomenon. So what we had were lots of direct impacts on the environment, direct impacts also on the different stakeholders and different activities that are based on the water and on the rivers. So first of all, we had a big decrement in national agricultural production, and then also some kind of restrictions that were, for example, needed in Po River canals, and also in other contexts, such as, for example, artificial reservoirs that were forced actually to decrease the discharges, and in this way affecting also hydropower plants. Then we also had the risk of having rationing of drinking water, even though this didn't happen luckily, and then also obviously the possible impacts on the ecosystems, so on the environment, and as a consequence, the possible biodiversity depletion that is actually our main interest in the partnership with Regione Lombardia. So, Regione Lombardia and also other public authorities were forced to enact some kind of regulations for requesting actually prevention and mitigation campaigns on the effects of water scarcity and drought on the territory. And it is exactly in this context that we were requested directly by these units of Regione Lombardia for having some kind of tools for supporting the public administration in informing actually the different stakeholders on the territory, because they clearly said that it's true that we can have lots of data from the field, but they would need something that was visible. So, for example, some maps in order to deliver correctly the message, and so letting the stakeholders on the territory understand the severity and the effects of water scarcity and actually drought impact on their own territory. So what we did was to, first of all, accept this kind of proposal, this kind of job, we can say, from them, and we had a big assumption of for our project that was the estimate as a parameter for drought condition of water surface extent variation, meaning that what we can see with our instruments, that is obviously based on remote sensing images and so by satellite images, is something that is the surface itself, and so we can see the extent and also have a sort of proxy of the extent of water in a certain area, and so we want to use this kind of parameter for estimating the condition and obviously the variation for understanding how it is the behavior of an area of interest. So we propose this kind of methodology for exploiting satellite imagery, and in particular this will be performed through sensor integration of two different kinds of sensors. So, first of all, we can say that also historically remote sensing techniques are widely used for detection of water. What we can say about, for describing, we can say remote sensing more very, very general. We know that it is a bunch of techniques that are non-destructive and that can extract information from a surface or from a territory, basically, it's more or less the same, basing on the response that we can draw and represent as an image. This kind of response will be different if we are dealing with radar or optical sensors or whichever other kind of source. Basically, we can distinguish between passive sensors and active sensors. If we are working with passive sensors, we can say that the output that we got from the satellite or in general by the sensor is something like a photo, so a shot of the real situation. While for the active sensor, we are giving an input. We can say we are sending an impulse, we can say, to the surface, and then we record the response of the surface itself. So how can we detect water? Obviously through a sort of pixel classification. We are dealing with the images, so each pixel has its own value, and so this value has a specific meaning depending on the kind of instrument, and so we can try to classify each pixel for understanding if it is belonging to a water class or not. As I said, we have two main categories of sensors that are used for this kind of issues. First of all, we have the optical sensors that consent to explore different visible and infrared wavelength for analyzing what we have. In this case, we have passive sensors, while we have the synthetic aperture radar that is a radar sensor indeed. And in this case, we have an active one in which we have the recording of the scatter value of the emitted microwaves. We can work with optical images by combining information on different bands in spectral indices, and then from this kind of spectral indices we can try to highlight actually the water features and so extract them. On the other side, with radar sensor, we have the bonus that actually water is responding in such a unique way so that we can easily distinguish water from the rest of the other surfaces and so of the territory, because it is working exactly as a specular surface, and so we can record very low values, and so what is depicted as a dark pixel. We can work on these images by photointerpretation or thresholding, so selecting a value that is defining the difference between a class and another one. And we can obviously have some kind of issues for the specific satellites and sensors. First of all, for optical sensors, we know that we have this kind of passive and optical source That means that if we have some kind of obstacle, and this obstacle may be also a cloud, we will lose completed information. You can see here an example on our area of interest in which we have indeed the presence of a cloud, and so we lose completed information that is behind it. And for radar sensor, indeed, we have another set actually of possible misclassifications that are based on some background noise, or maybe by the presence of water-like surfaces, so surfaces that react as water even though they are not water, or other kind of issues such as soil moisture that can be perceived as water even though it is soil. And you can see here this lead, for example, to an overestimation of the water presence, apart from the other characteristics of the river that you can see is not exactly mapped in either of the two cases. Anyway, what we decided was to try to exploit this sensory integration, try to understand if combining the two different sensors we could obtain better results in which one of the sensors could overcome the issues of the other and vice versa. So here we have a schematized methodological workflow of the methodology. So first of all, we have the input images from Sentinel-1 and Sentinel-2, so radar and optical images, the creation of two thresholding water map that was, we can say, some kind of reference solution, some kind of reference map for water classification. We have that are basically the ones that you saw before in that error slide. And we use two different spectral indices for the optical that are the NDWI and the SWM, that stands for Sentinel Water Mask. And then these three different bands, so the one from radar and the two from optical, are stuck into a supervised random forest classification. And so we are using machine learning, and specifically we are using a supervised technique. This means that we should provide something that is obviously training the algorithm and that is representing the ground truth, you can say. And so we give to the system a polygon training set that we draw directly from via photo interpretation from RGB images. So we obtain a classified water map, and then we validate it through a set of 5,000 randomly selected points, for which one by one we checked actually the correctness of our classification. And aside, we also have a comparison with other kind of data coming from the field that are coming from hydrometric network system that we will see in later on. So everything was performed in the Google Earth Engine context, and we know that this is a cloud-based geospatial data service that is provided obviously by Google and coded in JavaScript language, and also operating from our side on JavaScript language. And it gives lots of possibilities because, first of all, it is not requiring that we download data, but it is providing all of those data that are open data. And first of all, and most of all, obviously, all the computational time is shrunken because we are working with their cloud. Okay, sorry. And for the data, we are working with the public administration, so we decided to use open data and open satellite data. So we went to Copernicus, that is providing us information from different kinds of satellites. So we selected the Sentinel-1 synthetic vector radar for radar imagery and the Sentinel-2 for optical imagery, using specifically the multispectral instrument that is mounted on. So let's have another kind of specification on this, on the characteristics of the two sensors. We should understand that we are working with images coming from satellites. Obviously, we have different satellites, meaning that we have different orbits. So it's very difficult that in the same day we can have images covering the same area, the same exact area. And this is also true that, for example, the optical source can have some kind of errors and issues for a single image in a single area. So what we wanted to do was to obtain a sort of pre-filtering process that selected only images that helped us in covering completely the area of interest without cloud. And for doing that, we accepted the possibility of mosaicing images coming from different dates. So what we can say is that we will work not on the pure images, we can say, coming from the satellite, but on synthetic images that are created by mosaicing one or more images if it is needed. Specifically, what we can say is that this is obviously possible just because we are working with such a slow process as the drought evolution in a river, and so we still know that we cannot merge information coming from such disparate dates, but for example, we are staying in the interval of 1 or 2 weeks for each of the iteration. And so we can go on. As we said, we had the spectral indices evaluation and the reference water mask or production. And then we have the sensor integration its own, and that is made by the supervised classification. As I said, the first attempt was made with a random forest algorithm with 10 decision trees, and the input were performed. It was established in this stacked image of the 3 bands that we can give as input. So we have the run of the algorithm and the obtainment of the thematic map of water coverage, and then also an estimate, as I said before, of water surface in the area of interest. Clearly, we are not saying that those data and those numbers actually will exactly represent the square kilometers of water in that area, but they are needed to have a sort of proxy, as I said before, in order to be able to compare different dates and understand if the behavior that we can recognize from satellite is actually reasonable or not. And then, as anticipated, we had also the validation pixel by pixel for some kind of extracted point. So, going to the study case, obviously, as I said, the Region Lombardia interest is to monitor their principal rivers, and we know that the Po River is the main and major river in the Region Lombardia. So it was quite easy to select it as a first case study. Po River is very instrumented, you may know that. So for example, we have the hydrometric network that is managed by Agenzia Interregionale per il Fiume Po that is providing us with data, centimetric data, even available each 5 minutes, but then depend on the section. So this is very important because those information are the only information that we can have from ground. We cannot be sure that pixel by pixel we had in that day water or non-water in our map, basically, but we can be sure of the presence of the datum of the level of water in the specific date of reference. So it was needed such of information for corroborating our results. So we decided to focus on a stretch of the Po River that was contained between 2 different sections that are instrumented, so from which we could extract this kind of information, and also the selection of the representative stretch was performed in order to be sure that the response that we could find on the territory was coherent with the results of our work. So we wanted to have a sort of peculiar stretch in which we had multiple bands and which we have lenses of terrain within the river, and most of all a section geometry that was suitable because we are working with the detection of the extent of the water, so a longitudinal, we can say, way for measuring the river width. But it is important to understand that depending on the shape of the section itself, a longitudinal variation in the width can or cannot correspond to a vertical, say, variation. So it is important to understand if these 2 behaviors could be paired or not. So here we have highlighted the sections that we use between Spessa Po and Piacenza. Here you can see also the sections of the 2 areas that we considered. We know that these sections were among the most impaired by the drought event, and the data are actually confirming it. We are reporting official data coming from the official bulletin. So, for example, in Spessa Po, we had a huge decrease in the flow rate, while in the case of Piacenza, we had official indices such as the standardized flow index that stated the critical situation of critical drought. Here you can see, actually, one of the first results, we can see neat results of our procedures. So you can see that in this case, the river is quite well mapped. We can recognize clearly the extent of the water, and most of all, we can also see that we have no problem in the proximity of clouds, as much as we do not have any problem in case of the presence of the fields. So we have no overestimation of water that was coming from the optical, from the radar source. Sorry. We have here an estimation of accuracy that is higher than 90%, and then an estimate of water extent of 13.48 square kilometers. We can go on with the results of our multi-temporal analysis that was conducted on a couple of dates for each year between 2016 and 2023. And first of all, we can recognize, as expected actually, behavior that is cyclic, behavior, and it's coherent with the seasons. But if we want to observe 2022, let's focus on this area that I'm pointing out, and you can see that we have a huge decrement of water until 2023. This is obviously confirmed by the results, the numerical results. So we can say that the water surface that we estimate as a sort of mean in 16 square kilometers, and we had the worst condition of August 2022, so in the middle of the drought event, and in the middle of summer, so it's quite expected, we can say, while the best situation, and I would say not the best one, I mean the best one in terms of quantity of water that is extracted in May 2023. Why is that? We can have here a direct comparison between the two extreme conditions, so the one with less water and the other and the opposite one. Well, obviously, you may remember that this area was affected by a double flood event last year, and so it is exactly the reason for which we find such a great quantity of water is because actually we used images that were taken in the week after this kind of event, specifically the second event of flood in the middle of May 2023. So here we have the attempt for correlation between the water surface extent estimation and the measured water level. As I said before, it was important for us to understand if we can find a sort of pattern that confirmed that the behavior of water extent is also paired with the information on water level, and indeed it is, because we found a R-square of 0.84 for both of the section that we were studying. And now I will take some more minutes for describing the evolution of this day's project and specifically what we are calling towards automation. Indeed, as I said, we want to provide at the end of the work a real instrument in the hand of the general users. And this means that we should provide an instrument that can be used even by people that are not expert in remote sensing, non-expert in GIS, and in general that should only request for some kind of general information to the system that should be able autonomously to give the answers and to give back especially the mapped water extent. So we did this automatization process, actually we performed it with some kind of ideas that some ideas that we have. First of all, the automatic thresholding, because as I said before, we can try to understand the values that divide one class of pixels from the other one, and this is made usually by imposing to the system a certain threshold that indeed should be defined, for example, in literature or with specific analysis on the image. We found this also algorithm that is an automatic thresholding algorithm for which, given bimodal images, the system is capable of extracting autonomously the value that maximizes the interclass variance, and so actually the value that can be used for splitting the two different classes, so water or non-water. The issue in this case is that this kind of algorithm is working in situations in which we have a bimodal image, and we know that in our case we are not in such a situation because we are in an RGB image with such a different condition, with a set of different conditions, and so we use the modified version of the algorithm that is the so-called BMAX also, that is first of all segmenting and dividing as a sort of chessboard scheme. I hope you can see it actually from the image. So we have this division in cells of the overall image, and then the bimodal variable is estimated for each of the cells, and only the cells that result to be bimodal actually are used for establishing the thresholds. Okay, so this is the main concept for trying to automatically extract water information from the tree input. So the other aspect is obviously the fact that we train the algorithm in the first moment by drawing polygons. So we want to avoid that the user should for each iteration, draw by himself the algorithm, the polygons themselves. So what we want to do is to extract automatically training and test set from the images, and so we need, obviously, in order to have something for to have a data set, we can say, from which we can extract this information, we need to be sure that we have a data set containing only purely water and purely non-water pixels. So how did we get to this point? First of all, each of the three bands was classified through the Vmax also algorithm. So we obtained three masks, we call them masks actually, that are, we can say, rough maps in which we have only the pixels that are perceived for each of the three indicators as water and non-water. Then we also asked to the system, but which of these pixels are actually in common in all the three information that we are giving as input? So which are the common pixels, which is really water, basing on what we have as a data? And among these, which are the pixels that remain consistently classified in the same class for all the time interval that we are studying? And in this way, we could extract only the pixels satisfying these queries, and so obtaining a new reliable mask. At this point, we had a mask that is not the final map of classified water, but it is a mask containing only pixels that we can rely on for extracting pixels that are water pixels and non-water pixels. I'm sorry if I repeat myself, but still, it's quite important to stress this aspect. So training and test samples are randomly extracted within a certain percentage of points that was calibrated in 0.02% of the pixels of the area. And as we can see here, for example, we can have a look to the final mask, to a detail of the final mask, in which in yellow we have the pixels that are perceived as surely water in the period of reference still, in white the ones that are perceived as non-water, and then in light blue, the pixels that we extracted for training the algorithm, and in red the other class ones. Other aspect of our work, and that it should be also developed, so I put here this draft line for letting understand that it's not something that is at the moment developed. We are working for the automatization also by providing a single application, a single web app for having this kind of procedure automatically done. So this would be more or less the interface for the user, and by simply inserting some kind of information such as the date of interest and the area, then the system itself will give back some kind of information such as the map water and also water differences in the area that is considered. Lastly, basing actually on the evaluation that we did, was trying to perform a comparison between different machine learning algorithms, and also we wanted to understand if actually our work was useful or not, because we also tried to classify everything with a single sensor, so only optical and only radar images, and we compared this kind of results. First of all, we can recognize that not always the sensor integration is the best solution for mapping water, and this may seem a little problem actually from our point of view, but you can also notice that the best performing one, that seems to be the Sentinel-2, actually has a huge decrease of efficiency, of accuracy, so of reliability actually in one of the dates that were chosen. And that's why, and that's because we can suppose in that date there was the presence of cloud. So we can say that in general, in case of perfect atmospheric condition, the Sentinel-2, so the single sensor optical, is the best solution. But then obviously we should be aware on the fact that obviously this instrument is not always performing and delivering results. So we can say that the combination is actually the optimal result because it is giving good results in all of the different situations, okay? Given this potentiality, as we said before, of this capability of overcoming the issues of the single sensor through the integration. And then in this comparison, we also discovered that the support vector machine algorithm seems to be the best one for our case. So all in all, we can say that this proposed integration actually seems to work, and is also methodologies that can be replicated for whichever couple of sensors that are optical and radar. Then the validation also proved that the results are quite good, and the multi-temporal analysis showed that actually these kind of results are very trustable, both in case of flood and in case of drought. So we can say that actually it is working in the whichever condition, at least for our case study. Also, the correlation between water surface and water level is corroborating the results, but still we should be aware that everything is based on data, obviously, as everything in our work, and it is based on imagery. Imagery can be imperfect, so can have some kind of issues, and so basically we should be aware that this kind of work may not properly work and deliver results in case of problems with the original data, and it's quite obvious. Then this methodology is, until now actually, can be used for short and medium time monitoring, but not for real-time monitoring, because as I said before, we need several images, and so we cannot take the input as a real-time input. And then the other issue is that Google Earth Engine platform, that is the one that we used, also that we will use probably for the evolution, so for creating this kind of web app, is a proprietary platform, and so in case of real use from the side of regional authorities, they should establish some kind of agreements. For the future, we want to refine the code with some kind of development, for example, in the window selection enhancement. Then we want to also validate and prove this kind of evaluation for different case studies, both actually different case studies within Po River and also on different rivers with different morphologies, and then we want to produce the final web app. The work that I presented was published in its first part, actually, was published and presented in the Geospatial Week in Cairo last September, and then the advancement, we can say, with the automation has been submitted actually for another conference this year, so we hope to have also that one published as soon as possible. And I think it was all on my side, so thank you for the attention.